When it comes to performance, an engine is only as good as the air it breathes. In the field or on the job site, engines live in a hostile atmosphere of dirt, dust, sand, and chaff. Successful preventive maintenance starts with stopping these contaminants before they wear away power and profit. The more air you can put into an engine cylinder, the more power it develops. Traditionally, adding more air meant adding cubic inch displacement with a larger cylinder and piston, like this. But as power goes up, the size and weight of the engine finally becomes impractical. The modern way to add more air is to turbocharge the engine. A turbocharger is simply a blower that rams more air into the cylinder by compressing it. The more air is compressed, the hotter it becomes. On more powerful engines, we add an intercooler to cool the air. Now we can pack a tremendous volume of air into the cylinder without increasing engine size. A naturally aspirated engine consumes about 13,000 gallons of air for every gallon of fuel. A turbocharged engine uses even more air. And on more powerful intercooled engines, air consumption is still greater. The air we breathe is free, but the free air an engine breathes can be very costly. The more air an engine takes in, the more work the induction system must do to keep contaminants out. The typical modern air induction system, equipped with a dry air cleaner, is designed to provide air in the right quantity and quality. The system consists of the pre-screener and pre-cleaner. Intake air then moves to a primary element, usually the final barrier to particles not removed by pre-cleaning. Many induction systems include a safety element to prevent serious engine damage should the primary element fail. The system directs air to the intake manifold or turbocharger through pipes and connectors, which seal the clean processed air from dirty outside air. The equipment and its application influences the location of the point where air enters the intake system. When a vertical stack is used, it is positioned carefully to avoid drawing exhaust fumes and is protected from rain. The pre-screener is a simple device to prevent leaves, chaff, lint, and other large contaminants from entering the pre-cleaner and air cleaner. On a vertical stack, it's usually part of the pre-cleaner or rain cap. A pre-cleaner is required to filter out larger dirt particles before they reach the primary element. Otherwise, the primary would have to be unreasonably large in size, and it would require servicing too often. When the air intake is located under the hood, pre-screening of lint, chaff, and leaves is usually accomplished by the grill screen. It is important that this screen be in place at all times. Pre-cleaners mounted behind the grill screen may be an integral part of the air cleaner canister. Dirt separated by the pre-cleaner is discharged at a rubber unloader valve or trapped in a collector bowl, which is periodically emptied. This type directs the dust to the muffler, where it is expelled with the exhaust. Pre-cleaners will remove from 80 to 90% of all contaminants before they reach the primary element. But what gets by can rapidly destroy an engine unless it is completely eliminated. And this is what gets by the pre-cleaner: a fine powdery dust, very much like talcum powder. It feels smooth to the touch, but engines are machined to such close tolerances that these dust particles will destroy them. Now, mix a bit of this silken powder with some engine oil. It feels slick, almost like a lubricant. Now, let's rub the glass with a piece of metal and see what happens. In just a few seconds, the erosive wear of that silken powder has already begun. And if this dust enters an engine, this is the result. Lost performance from a little dust, a little downtime that could be holding up other scheduled work, the costly man-hours of labor, the replacement parts, losses that could have and should have been prevented. That's why the primary element is so important. Here's how it works. The remaining dust from the pre-cleaner is removed as it travels through a replaceable paper cartridge. These pleats greatly increase its effective surface area. Frequently, a safety element is used in addition to the primary element. Its only function is to protect the engine if the primary element fails. However, because of its small size, it will clog rapidly. Never rely on the safety element to do the primary element's job. As dust is collected in the primary element, airflow to the engine is gradually restricted. This restriction indicator provides a visual indication that the filter element needs cleaning. Some restriction indicators actuate a warning light on the instrument panel to signal for servicing of the air cleaner. Dry element type air cleaners are growing in popularity because they're highly efficient, relatively small, lightweight, and because they can be mounted in any position. Now, let's discuss the oil bath cleaner. The oil bath air cleaner directs incoming air down through the center tube into the oil cup, then up through the filtering element and out to the intake manifold. Dust is trapped in the oil in both the cup and the filtering element. Dust in the filtering element is washed to the bottom of the cup. When the engine is running at slow speed, the oil is elevated only partway into the filter element. As the speed increases, it is elevated to its maximum. The oil bath cleaner is at maximum efficiency at rated engine speed only. The oil bath cleaner must be mounted in an upright position. If tilted too far, oil would be drawn into the engine. To clean an oil bath air cleaner, first remove the oil cup and pour the oil out. Then, clean the sediment from the bowl. If the fixed element becomes restricted and service is required, it must be removed. Clean it by soaking and flushing thoroughly in a solvent and blow it out with compressed air. Never use a steam cleaner. It will look clean on the surface, but instead of cleaning, the contaminants are driven deeper into the element. This creates a hidden sludge and restriction in the element's center section. Inspect the center tube for any restrictions. Also, be sure there are no holes, loose joints, or restrictions in the ducting between the air cleaner and the intake manifold. Fill the oil cup exactly to the level line with the same quality and weight oil used in the engine. Never refill with used oil. Now, servicing the dry air cleaner. It's called for periodically in the operator's manual. Of course, the dustier the working environment, the more frequently inspection and service are required of the entire system. So let's talk about servicing the system, starting with the pre-cleaner. Some pre-cleaners have a clear plastic collecting bowl, so you can readily tell when it needs emptying. Allowing this pre-cleaner to become overloaded places a great burden on the primary element. If the dirt from the pre-cleaner is expelled by an unloader valve, the valve should be examined closely to make sure that dirt hasn't plugged the opening. Check for any tears or cracking and replace the valve if necessary. Some pre-cleaners have an aspirator which draws contaminants to the exhaust system, where they are expelled. This assembly needs occasional checking to assure that leaves or other debris aren't blocking the way. The aspirator consists of several spiral tubes called vortex generators installed in the air inlet. Notice that they protrude into the pre-cleaned air compartment. This compartment leads to the primary element. Air passing through the tubes is spun by the vortex generators, causing dirt particles to be thrown against the walls of the larger tubes and drawn off by the vacuum from the exhaust. Now, let's service the dry air cleaner. The heart of this air cleaner is its paper filter element. When it needs cleaning, follow the procedure outlined in the operator's manual. First, simply tap it with the hand while slowly rotating it. This will loosen the dust packed in the paper pleats. Never tap the filter on a hard surface. Here's what happens. The filter is so heavy with dust that banging it on a hard surface will break the paper element and allow dust to enter the engine. The second step is to blow out dust with compressed air. Direct, clean, dry air up and down the pleats, blowing from inside to outside. Use a low pressure, about 30 pounds per square inch. Keep dust from entering the inside of the element. For a completely thorough cleaning job, follow a third step. Use a non-sudsing detergent and soak the element. This step must be followed if the element is coated with soot. Never soak an element in fuel oil, gasoline, or solvent. Then, after soaking, use a tool such as this, designed to fit on the end of a water hose. Rinse from the inside out with clean water. Shake out the excess water and allow the element to air dry for at least 24 hours. Never install an element that is not completely dry. Moisture and dust form a muddy film on the element that restricts air movement. Following these steps, an element can be cleaned as many as 6 times before discarding. Many operators have a spare element to use while the other is being serviced. After checking for dents, nicks, or tears, check also for holes which could pass dust. Place a light bulb inside the element and look toward it from the outside. The smallest pinhole is reason enough to throw it away and install a new one. Finally, check the element seals to be sure they're reusable. Before reassembling the air cleaner, inspect the safety element in place for traces of dust. Unless there is evidence of a failure of the primary element, the safety element should not be removed except for its recommended annual replacement. At that time, don't attempt to clean it. Throw it away and install a new one. The air restriction indicator should be reset, if of the mechanical type, when the air cleaner is serviced. If the indicator doesn't work properly, replace it. Don't over-service a dry element air cleaner, only when the restriction indicator says to. Over-servicing exposes the induction system to possible contamination and the element to possible damage. If there's an occasion to disassemble the intake piping, check for evidence of dust entry at every point on the clean air side of the system. Every connection must be dust tight. The clean air side of the intake system should be checked regularly for leaks. If they should go undetected, serious damage will occur without prior warning. Beware of a damaged element, a loose or torn seal, improper element seating, loose connections or clamping at hose or pipe joints, hardened or cracked flexible connectors, cracked or worn spots in steel pipes, or a damaged or missing restriction indicator device. We've seen what happens on the clean air side of the system from undetected leaks or a failure of the air cleaner. Engine failures, a direct result of worn parts. But suppose the elements in pre-cleaner are doing their job. If you fail to service them, whenever servicing is indicated, the engine can still be damaged. As the particles begin to cause excessive restriction, a loss of power isn't immediately noticed, particularly if the engine is turbocharged. However, fuel consumption will increase, demanding additional air from the turbocharger. There will be a dangerous rise in cylinder and exhaust temperatures. Oil consumption will occur. The result? Damage to pistons, rings, valves, even the turbocharger itself. Repairs can cost plenty. Lost production due to downtime costs even more. Performance and power, designed and built into every engine. Proper preventive maintenance of the air induction system will assure clean air that engines may live to perform demanded applications. Every power plant has an optimum operating temperature to make best use of its power. We humans function best at 98.6 degrees Fahrenheit. Raise that temperature a degree or two, and performance falls off rapidly. So power plants need some sort of a cooling system. There's air cooling, and there's liquid cooling, which normally uses water as the major coolant source. Engines have the same problems with heat. Of the total fuel an engine burns to produce power, only about 1/3 of the heat can actually be used for power. What happens to the other 2/3 of the heat engines produce? About 1/3 goes out the exhaust, but the other 1/3 must be removed by the engine's cooling system if it's to operate properly. So the cooling system is an extremely important part of the engine. Kept clean and in good repair, it helps keep the engine operating at the proper temperature. The basic components of the cooling system are the radiator, pressure cap, the fan which draws air through the radiator, the water pump, coolant passages within the engine, the thermostat, and connecting hoses and pipes. Each of these components is designed to match the job it must perform. Together, they work as a balanced team to control and circulate the final basic component, the coolant, through the engine. The coolant and the cooling system are interrelated. The coolant must help maintain the cooling system components if the system is to accomplish its vital job of regulating engine temperature. At full load operation, flame temperatures in the engine's combustion chamber can go as high as 3,000 degrees Fahrenheit. The piston, liner, head gasket, valves, and injector, which are directly exposed to the heat of the combustion, would melt if it weren't for the cooling system. Heat is generated in the engine from the burning of fuel and from the continuous friction of the many fast-moving and close-fitting parts. The coolant circulates around and past high-temperature areas through passages in the engine. The heat is conducted through metal to the coolant, which flows to the radiator. There, the heat is dissipated to the air. So the cooling cycle is fire to metal to coolant to air. Simple enough, but very costly if the system and the coolant are not properly maintained. Let's review this in more detail. Rust occurs in the engine when water comes into contact with cast iron. While a good rust inhibitor will not rid an engine of existing rust, it will prevent rust in a new engine. Quality ethylene glycol antifreeze contains rust inhibitors in sufficient quantity to do the job. Mineral deposits occur when water with any mineral content comes in contact with hot metal. Water boiled in a tea kettle is a good example of this chemical reaction. This scale or deposit builds up on the metal and creates an insulation barrier that prevents heat from moving rapidly through the metal into the coolant. In fact, 1/48 of an inch of mineral buildup equals the same insulation characteristics as an additional inch of cast iron. The buildup on this liner equals 1.5 inches of cast iron. Chlorates prevent these mineral deposits. A good rust inhibitor contains sufficient chlorate to stop mineral buildup. Mineral deposits and rust damage the engine. Typically, they coat metal parts and cause hot spots. They wear out water pump bearings and seals and cause piston, ring, and liner failure, as well as failure of gaskets and packings. Mineral deposits and rust clog the oil cooler and radiator, and they reduce cooling efficiency significantly. Another culprit that causes clogging is oil and grease. This comes from leaking gaskets, poor servicing techniques, and pouring water into the radiator from an oily container. Remember that oil breaks down anti-rust and anti-mineral additives in the coolant. Water becomes acidic whenever metal dissolves in it. Seepage of head gaskets allows combustion gases to enter the coolant and increase its acidity. The acid then attacks all metal and rubber parts of the cooling system. If allowed to go unchecked, this chemical process accelerates and becomes a vicious cycle. Again, a good rust inhibitor will neutralize acid. The best insurance against rust, mineral deposits, and acid is an annual program of preventive maintenance of the cooling system. As we've mentioned before, rust inhibitors only keep the rust from forming. They don't get rid of it once it's in the system. So once a year, drain out and discard the old coolant. If the coolant drained out was rusty, use a good flushing agent to rid the system of rust. The system should be thoroughly flushed clean. In extremely stubborn cases, you may need to remove the radiator for chemical or mechanical cleaning. Now fill the radiator with clean, mineral-free water and antifreeze or reputable rust inhibitor. If you have hard water in your area, purchase soft water for the system. It's relatively inexpensive, far less costly than the damage hard water can do. Never add water to a radiator that has been taken from a drainage ditch, irrigation canal, or similar source. Sediment from the water settles around the lower portion of coolant passages in the block. This prevents heat transfer from hot areas, such as the cylinder, and can result in costly repair. Use a good brand of ethylene glycol-based antifreeze. This is permanent antifreeze, which simply means that it won't boil away, not that it lasts forever. Add compatible inhibitors if necessary, but remember, most good antifreezes already contain them. Once the system is filled, it's essential to maintain coolant level high enough to prevent air from entering the system. Air is a good insulator, so it retards cooling. And since it contains oxygen, it accelerates rusting and corrosion. With the high volume of coolant flowing through the engine, small air bubbles want to stay entrapped in the system. Special baffling in the radiator top tank removes the bubbles from the system, and this is called de-aeration. Without sufficient water above the baffles, they cannot do their job. Coolant flows through the system with velocities high enough to give good heat transfer and with capacity high enough to carry the heat away, depending on radiator and water pump size. Coolant flows between 1/2 and 3/4 gallon per minute per 1 horsepower at the engine flywheel. Therefore, an engine with 100 flywheel horsepower might have a total coolant flow of about 65 gallons per minute during full load operation. Maintaining the coolant assures the maximum life of all components of the cooling system. It's the one thing all these components have in common. But now, let's discuss the components in more detail. The radiator is where the coolant releases heat to the atmosphere. For the radiator to do its job properly, it must be kept clean, inside and out. The pressure cap has two functions. It allows pressurization of the system to raise the boiling point of the coolant. And it allows air to enter the system after engine shutdown. Each 1 pound of pressure per square inch will raise the boiling point of pure water 3 degrees Fahrenheit. So, as an example, a 7 psi radiator cap increases the water's boiling point by 21 degrees. Thus, a 7 psi radiator cap will raise the boiling point to 233 degrees at sea level. As the altitude increases, the boiling point is reduced. The pressure cap must be of correct specification for the system, and it must seal where it contacts the neck of the radiator to allow pressure buildup and prevent loss of coolant from the system. To check the radiator cap for correct opening pressure, use this special radiator cap tester. The fan's size, design, and RPM determine the volume of air moving through the radiator to remove heat. The fan depends on fan belt tension to maintain its optimum speed. The water pump is required to circulate many gallons of water through the engine and radiator every minute. In the case of belt-driven pumps, the belt must be correctly tensioned to assure peak efficiency. Connecting hoses should be checked periodically since they deteriorate with age. Usually the failure occurs inside the hose where it can't be seen. Even though a soft hose might appear normal on the outside, it may look like this on the inside. If it does, it will eventually collapse and restrict water flow at high water pump speed. Many engines are equipped with a crankcase oil cooler, which is a radiator-like core enclosed in a housing. Oil flows through one portion of the core, and coolant flows through another. This compounds the job of the cooling system, but fortunately, it's designed to handle this additional load. Many modern high-performance engines are equipped with turbochargers, and, for even more power, turbochargers with intercoolers. Oil that flows through the hot turbocharger must be cooled in the oil cooler. Since a turbocharged engine burns more fuel, there's more heat to be removed by the coolant. An intercooler is a radiator-like unit located in the intake manifold. Coolant circulates through its core and removes heat from the intake air that has been heated by the compression of the turbocharger. The result is still more work to be accomplished by the cooling system. As you would expect, it is designed accordingly. The thermostat is a heat-operated valve which controls coolant flow to maintain the correct engine operating temperature. During engine warm-up, the thermostat remains closed. This allows coolant to continually recirculate through the engine cooling passages without passing through the radiator. So, the engine warms up faster. During light engine load operation, the thermostat partially closes to prevent subnormal operating temperatures. This word of warning: never allow an engine to operate without its thermostat installed. Most engines have a normal operating temperature of at least 180 degrees Fahrenheit. When an engine runs below best operating temperature, fuel that hits the relatively cold combustion chamber or cylinder walls will not burn. This raw fuel dilutes the lube oil on cylinder walls and helps carry contaminants into the crankcase oil. This excess fuel also reduces the oil film thickness on the walls, which in turn allows faster wear of rings and liners and increased blow-by. This contamination results in stuck piston rings. Cold engine operation results in condensation in the crankcase, forming sludge in the oil, eventually resulting in failure of lubricated parts. This is especially true of pistons and crankshaft bearings. A properly functioning cooling system performs the critical task of removing heat from the engine. In turn, a properly conditioned coolant is the best way to maintain cooling system components for long, trouble-free life. Modern high-horsepower engines require more cooling power than ever. Proper preventive maintenance of the cooling system will contribute to top machine performance, everyone's goal. Efficient cooling systems that engines may live.